Hi. So now let's have a look at what would be the Gomorry Fractional Cutting Plane method. Being that sort of one example of a possible cutting plane method for LPs, for IPs. Right, so once again, let's look at our IP defined by search. And now I'm changing things slightly because we're moving towards the realm of Simplex Method. So I'm putting that the definition of my feasible set is a collection of integer variables that are non-negative, such that I have a collection of equality holding here. Okay. Remember, it's been a while now, but we're gonna re-tap on that those definitions we did for the Simplex method. So so X on the LP relaxation of this thing, what I'm getting, these optimal solutions characterized by a basis B, formed by the matrix A. So basically you can think of a basis B being a collection of columns of A. So if I have these columns of A that I selected for my basis, and I join it with my other columns, and I'm calling this the N, referring to the non-basic variables. So by the way, this is just you can read this as the horizontal concatenation of B and N, because B are the columns of A that are in the basis, and these are the remaining columns, and then when I put them together, I get my matrix A again. We've seen this before. And then X has this component associated with basic variables, and the components with the non-basic variables are all 0. And XB can be written like this: is our basic solution, Xn is 0, non-basic variables, and so on and so forth. So we're seeing all that. You just, kind of bringing back the past, because we're gonna need this when it comes. So the system AX equals B can be opened like so, or we can have it written like this. What we did before, we moved this to the other side, so we can say the XB is written as a function of the non-basic variables. And we can also look at this. It's just as a reminder of what we display in the full form tableau. So basically, this here is the same as this, because this would be B minus 1. This would be B minus 1 that pre-multiply BXB plus NXN equals B minus 1 that pre-multiplies B. And this, when you distribute this, these two terms become the identity. But I can backtrack and have something like this. And this is what you see in the tableau form that we showed before. So what we're gonna do is I'm gonna get these elements in a given row I of BI inverse B times A. And I'm gonna name the right hand side of that row AI 0 with this bar. Okay, so you can think of this going on my tableau and picking a row, and the row would be on the left hand side the elements of this, and the right hand side would be that element for a given row I. And so when I look at the solution, for this, the actual solution for my problem, my integer problem, what I'm looking for is something that can be written in this form, where the x is an integer. So, and if I want to write this like component-wise, so I have this, it will be this row-wise, and that summation here becomes simply this. Okay, using the notation of A bars, and then I'm asking my axis to be integer and non-negative. And this is just to remind you what I and J are. I am a set of rows, J my set of columns. IB is my set of indices, or basic indices from my G variables, and my IN are my set of non-basic variables, which is basically the set of all variables minus set minus of those that are in the basis. I'm sure you're familiar with that after doing homework 3 and implementing the simplex method. So, but anyway, I just wanted to make sure the notation is self-contained here if you happen to not remember these anymore. So the LP relaxation will have this optimal solution like so, but it might be so that it's not integer. And if that is the case, it will be because this term is not integer, right? Because remember, these are all 0 because they are non-basic. That's why you write basic variables as a function of non-basic variables. And then with this disappearing, you have that xbi is equal to this. Remember that this is just b minus 1b at the row I. And if this is fractional, then it means that your solution of your relaxation is not optimal, is not satisfying the integrality condition. So it's fractional. And then what you want to do is to find the inequality that will separate that. So if you have a row for each this is fractional, we can solve our separation problem, which typically means finding a hyperplane that will separate this fractional solution from the set of feasible solutions. And we can do that by generating what is called the Chvátal-Gomory cut, which is generated following the Chvátal-Gomory procedure in this context. So you can see that I'm just writing my basic variable here, and then I'm rounding down this, and I'm rounding down that to generate a valid inequality. Notice that by doing so, this is a valid inequality for x, but not necessarily for the formulation p. Okay? Because we're going to be using this in conjunction with the simplex method, so that means that what we have is we're going to have to replace this from with writing it as a function of the non-basic variables. So, and how do we do so? Well, we just replace this with the original form of xb, which is that, and plug this in this. And after some suitable reordering, we obtain this constraint, which is written only in function as a function of the non-basic variables, right? And has this. It is known as the Gomorry Fractional Cut. So you just name this f. So what is going on here is that we're basically setting this up to come and add a slack variable here. So this has the right form to go straight into your simplex method, and then lead to something that can be solved using dual simplex, just to give you some spoilers. And you can see that it's not that hard to see that this is immediately removing the current LP solution if this happens to be fractional, right? Because what's going to happen is that this is clearly greater than 0 because this thing is fractional. But at the moment, because now you've written everything in terms of the non-basic variables, this all here is 0. Because these are all 0, they are non-basic. So it turns out that, this constraint is violated. So if you just found a constraint that is violated, you found the separation, you solved the separation problem. So you can do this very efficiently. And that's the key for the success of a, efficient cutting plane method. It's having a separation problem that is efficiently solvable, or being able to find the separation hyperplanes efficiently. Okay, so this is just a nomenclature thing. This is the sometimes referred to the Chvátal-Gomory cut, and this is the Gomorry cut or the Gomorry Fractional Cut. And you most often see these with this name in the. Sometimes they're only called fractional cuts, but this basically means that these are the cuts that are generated just you looking at the fractions, the fractional parts of the coefficients. As you can see, that this would also mean that we're looking at the fractional part of these as well. So they are different. They are different animals. So some remarks here. Like I was saying, this is not satisfied because this is strictly greater than 0, and this is going to be 0 at the current point. So you are separating the solution of the linear relaxation from the actual feasible region, or you cutting it out at least. This is also something interesting, but sometimes it's hard to see that being the case here, but it's easier to see in the original cut. So basically it is saying that the slack, notice that this cut is derived from that just by simple substitution of xb, the basic variable xb. And we know that this is integer. And therefore this is slack should be integer as well. Okay. And because the slack here should be integer, and basically I'm just doing an obvious substitution and reordering, it means that for this it should also be integer. So that's how you prove this. That is absolutely not obvious. Okay. So that's it. Basically what we're gonna do is use these cuts and generate them over and over again as we keep finding fractional solutions when we solve our LP relaxations. All right. So here we go. So here is the numeric example we've been working with. You recall that, probably remember that when I solved the LP relaxation, I get that point there. And the next step here would be looking at what does that mean if you're thinking about the simplex structure, the system of equations around, associated with the simplex method, which I'm compactly writing here as a tableau, just so we can see the coefficients of the system. So here, x3, x4, and x5 are the select variables associated with these constraints. When I solved the LP relaxation, I found x1 20/7, x2 3, and x5 23/7. By the way, you can see that I removed this column. Well, one, because I needed space, and two, because now we're grown up enough to know that this row is going to be associated with this variable, because this is the coefficient 1 associated with the basic variable. So that's the basic variable written right here. So you can see that this is of the form that is, well, here with this on that side. Okay. I think it was actually here. There you go. This form. Or this form. I don't know. I just thought it's good to relive these again. So here, notice I have this variable that is fractional. So I'm gonna choose it arbitrarily to make it integer, meaning that I'm gonna generate. I'm gonna use the Chvátal-Gomory procedure in this to generate a valid inequality. And how does that go? Well, I'm gonna use as a cut generation procedure my fractional cuts, meaning that I'm gonna get this inequality, which is like here, and I will do something that looks I'm gonna end up with something that looks like so. And the reason for that is because when I round this down, I get 0. When I round this down, I get 0. So the A minus lowered rounded down A bars are gonna be just the fractional coefficients. But then something interesting happens on the right hand side. On the right hand side, I have 27ths. That's gonna be 2 point something. So taking 2 out of this as 14/7 minus 27ths minus 14/7 leaves me with 6/7. So there you go. And the next thing here is to convert this into equality constraint. So you can see I'm adding this. Recall that when we generated the cut, I had this form, right? So in order to make this an equality, I added slack with negative sign here. And that slack is what is in here. And because we want to do this in the context of dual simplex, what we're going to do is multiply this whole thing by -1. So that becomes, it gets inserted in I can add this constraint in my problem, and my basis, which grows, has already a basic variable to cover this new space in the basis. So you obtain this new tableau, and I'm here highlighting the new row that we added, because we multiply by -1 this negative, 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 and 1, and then you can see that you have a solution that is primal feasible, that is dual feasible, but it is not primal feasible. And you don't know how to solve that. Well, you come here, you go and apply a few iterations of dual simplex, typically not many, and you can carry on solving, getting to a new solution. I noticed I forgot to move this column to the other side. Sorry, it'd just be confusing, but bear with me. So now I optimized solved it with dual simplex, found a primal feasible solution, and also dual feasible. Also dual feasible, so it's optimal. And however, I still have a couple of variables that are fractional. So I have x2 and I have x4, both fractional. Right. So what to do next? Well, pick one of the fractional variables. I'm picking x2. And by the way, this is where we solved. This is exactly that first cut we generated. So this is the constraint that has just been added. See? And now if I solving the linear relaxation, so a couple of dual simplex steps, perhaps 1, 2 took me there, or 1, 2 take me there. Probably 1, 2, because that's more likely to keep dual feasibility. I think you have to be on the other side of the level curve here. So if you do this, this is probably not dual feasible. Anyway, yeah, and then we'll do the same thing. So generate a fractional cut for this constraint. You will see that this thing is gonna become 0 because 1 minus round down 1 is gonna be 0. This minus round down this is gonna be the same. This minus round down this is gonna be the same. So we get this sort of single, the cut only has this coefficient on x5, but that's fine. Same story, to make this positive, multiply by -1, add to my tableau, and re-optimize with dual simplex. You can see that, so the second cut I generated is actually this constraint there. And because I added this constraint and this constraint, now I have the convex hull. So when I solved this problem, the linear relaxation. Look what happens. All my variables are integer. All my variables being integer means that x1 and x2 is integral, and therefore I found a solution for my problem. So 2 constraints are enough. So one thing that might be remarkable is that, that kind of causes, it always amazes me when I'm talking about these, is that it's really impressive that the cut is exactly there and exactly there, right? And this is not necessarily the case. It tends to be the case when you have less and less variables. And maybe you are wondering at this point, is that, but how on earth that constraint that was on, the first cut was on on the non-basic variable. So this is x3 and x4. And how are you showing that on x1 and x2 plane, which is a valid question. So so here is, I put this in an example. You can just actually get it by simple substitution. So remember that. So I think I've done the easy one. No, I did only the first one. You can try and do the second one. So basically, this is how in the optimal simplex, how this variable x3 is returning as a function of x1 and x2. That comes from, I have to go a few slides back. That comes from this. So x3 being the slack of this constraint, I get x3 is 14 minus 7x1 plus 2x2, which is exactly what is in here. And x4 is the slack constraint of the other, is the slack variable of the other constraint. So basically the trick is get the expression for x3 as a function of x1 and x2, and the expression x4 as a function of x1 and x2, and then you're substituting the cut you generated. So plug x3 here and x4 here, and you obtain this. So basically you're projecting the cut on the space x1, x2, and that's exactly this constraint. You can do the same exercise with the one for x5. So we got half x5 is greater than or equal than half. Just get x5 and substitute with x5 equals 3 minus 2x1 plus 2x2. 3 minus 2x1 plus 2x2. So substitute this in there, and you're gonna end up with a formulation of this constraint, which I think is something like x1 minus x2 greater than or equal than 1. I think it's worth checking. And then you get there. So that's how you can show them. So yeah, if you want an automated way of doing so, here is a proposition that show how to do it. It's exactly just doing the substitution calculations we did, but in a more sort of concise form. Basically just, get that L row of B minus 1. I'm not using I because it's not B minus 1 A. It's just the matrix B minus 1. And then, calculate this vector Q, which is basically the differences, the fractional parts of the elements. So you can rewrite this cut as a function of the non-basic, which was originally a function of the non-basic variables. You can rewrite them in terms of the original variables by getting this vector Q and plugging in there. It looks magical, kind of like black magic at first, but if you do a bit of substitution, you can see that it's not that hard to convince yourself that you're going to recover how you can move from this to this. How can this become this using this vector Q? So that's that. I hope that was informative enough. So here is we're gonna do some exercises on cutting plane algorithms. And the reason why we looking at them is because even though they're not that successful by themselves, it turns out that combining what we see in the lecture, branch and bound, and cutting planes, we was just seeing this lecture, then we have almost all the ingredients that form professional MIP solvers, the ones you see out there, which we're going to be talking about in lecture 11 after we go through another a third sort of method in the bag of methods for solving large scale mixed integer problems included. All right, so see you in the next lecture. Bye bye.